Hello everyone, welcome to another video. This is your physics trainer Mockingbird. In this video, I'm going to show you how to prove the Lorentz reciprocity theorem. Like always, I'm not just gonna present the solution here. I'm gonna show you how to think through it. In this video, you will learn some key aspects. In this video, you will learn an interesting use of the divergence theorem combined with the Ampere's-Maxwell's law. You will also learn how surface integrals at infinity simplify using radiation electromagnetic fields. Plus, you will also learn how certain expressions simplify due to the presence of harmonic time dependence. So without further ado, let's begin to solve the problem. This problem is taken from one of my favorite books in classical electromagnetism. It's Modern Electrodynamics by Andrew Zangwill. I will attach PDF containing the problem statement in the description. However, I will read it to you in the video. So let's first define what Lorentz reciprocity theorem is. It is basically this relation, this integral relation. On one side there's a volume integral, on another side there's a surface integral. Now the problem statement tells us to suppose there's a time harmonic current density which produces two electric and magnetic fields which are also time harmonic, and the problem statement tells us to consider another time harmonic current density which produces another set of electromagnetic fields which also have harmonic time dependence. Now in part A of the problem, we have to prove this integral relation. Now I need to remind you that you don't need those time harmonic current densities and electromagnetic fields for this relation to hold. It's a quite general result where this surface in the surface integral is the boundary surface of some volume V. Now how to prove this relation? See, there's a surface integral on one side and there's a volume integral on the other side, and the relation that connects a volume and surface integral is divergence theorem. Sometimes you can connect surface and volume integral by using divergence theorem, but it doesn't always work. But let's see if we are lucky here. Now let's simplify the right hand side here with the divergence theorem. So with the divergence theorem, it would be simply this. And also there would be a divergence on the second term. Now, as you can see, there is a current density term present here, and we know that in Ampere's-Maxwell's law, we have the current density term on the right side, and on the left side we have the curl of magnetic field. So let's see if we can build up a connection between left and right side using Ampere's-Maxwell's law. So for that we need to have curl of B expression, right? So we need to work out the divergence here, and there's a simple vector calculus identity that I'm going to use here, which says that basically this. Using that, I'm going to simplify this right hand side. Now we will show a short proof of the vector identity that I just mentioned. Now I will show a short proof of the vector identity that I just mentioned. But if you already know the proof, then there's no need to watch this part of the video. You can just skip to the next part. So we need to prove what's the expression for divergence of A cross B. Now, we all know that the cross product between two vectors, it can be written using the Levi-Civita symbol, where the ith component of the cross product can be written in this way. And as we are taking the divergence, we'll need to take the ith derivative on the ith component of the vector here, which is this. Now a short introduction to Levi-Civita symbol. It has three indices, and if any of the two indices is equal, then this equals to 0. If the indices are not equal to one another, then if the permutation is cyclic, then it equals to minus plus 1, and if the permutation is anticyclic, then it equals to minus 1. Now cyclic permutation is like this, 1 2 3, and let's say we just don't switch any two positions, because if we switch, that would be an anticyclic permutation. But without switching, if we just rotate it like this, let's say we have a cycle like this, and we just rotate it, then we can have 2 3 1. This is also cyclic. But if we have, let's say, 1 3 2, then we have this anticyclic expression permutation, and the Levi-Civita symbol will just return minus 1. So let's operate the partial derivative on the vector terms, because the Levi-Civita symbol is just a constant. So we have this term, plus we have this term. Now let's take this in front of it. Now we can do a cyclic permutation, and you can find out, I keep it as an exercise for you, that this is actually a cyclic permutation of this Levi-Civita symbol indices. So there would be no sign change, and this would be like this. But remember, this is actually the curl of A's k component, and we have bk multiplied with the kth component of curl of A, then it's just b dot curl of A. But here, if we want to bring out the expression for curl of B, we need to do an anticyclic permutation here. So what we are going to do, we are just going to take the AJ out, and we are going to write it like this. And for similar reasons, we can write to be A dot. So that's a very short proof of the vector calculus identity I mentioned in the previous part. Now let's simplify the right hand side using the vector identity. Now let's simplify all these four terms separately. Now B2 del cross E1. So this is the Faraday's law, and it would be just this. But as we know that B1 is actually like this, there's a harmonic time dependence. So this term would be just I omega beta 2, sorry, beta 1. So let's just write the dot product here. And this term will have E1 dot del cross E2, and using similar logic we can show that this would be just I omega beta 1 beta 2. Now as there is a minus sign here, these two terms will cancel each other. So let's work out on the remaining two terms here and here. Now using the Ampere's-Maxwell's law, you can write this term as this. And let's simplify this. Now if you look into the expression of the Lorentz reciprocity theorem, you can already see one of the term is already present here. But what about the other term? Remember, the problem statement says that the electric fields have harmonic time dependence. So you take the partial time derivative of this electric field, you're just gonna get a minus I over omega in front of it. Using that, we can write this expression as this. Using similar algebra, we can write this term, which is another term in the expression of the integral in the previous screen. Well, we can write it like this. Now let's go back to the previous screen, and as you can see, the two terms here actually have opposite signs. So as we have calculated here, these two terms are present on both of these expressions, so that due to the presence of opposite sign there, these two terms will cancel each other. And so the remaining terms will be this and this. Using that, we can simply write this result. And that's actually the statement of Lorentz reciprocity theorem. And that's how Lorentz reciprocity theorem is proved. Now let's move into the part B of the problem. In part B, it says to specify the volume as a spherical one, which is large enough so that at the surface, at the boundary surface, the electric and magnetic fields are radiation electromagnetic fields. And with this assumption, the problem tells us to prove this relation. So how to proceed here? So first, let's just simply write the Lorentz reciprocity theorem because we have to use that. So it's something like this. E2 dot Z1 minus E1 dot Z2 equals to the surface integral of this relation. So as we have certain assumption in the statement that at the boundary surface the fields are radiation electromagnetic fields, let's see if we can simplify this surface integral to something useful that can be used to prove this relation. Now, the problem states that the current densities are inside this volume, right? And we are thinking about the radiation electromagnetic field's boundary surface. So for this case, the radiation electromagnetic fields have a simple representation, and that would be, say, both E1 and E2 are radiation electromagnetic fields, and they follow this simple relation, and same for the E2 and B2 pair. Remember, this only applies to the surface that is infinitely far away from the source. Now, using these two relations, I'm going to simplify this surface integral. Let's just separate out the integrand here. And this is our CB1, and this is B2. So here's a minus, and there would be a minus for the E2 field, so it would be plus, and this, and B1 crossed. And to apply the familiar backgap rule for triple cross product, we write it like this, and this. The backgap rule is a simple vector identity which is like this, which states that the result here would be B into A dot C, hence back, and minus C A dot B. So using that relation, we're going to get here. And we're going to get CB1 R1 dot E2. Similarly, we're going to get RE1 CB2 and plus CB2 R dot E1. Now for radiation electromagnetic fields infinitely far away from the source, we will have that the electric and magnetic field will be actually perpendicular to the radial direction. So what will happen is that this scalar product is actually zero, because two perpendicular vectors give scalar product as zero. And this is zero also, and these two terms are actually equal. So this whole integral is actually zero. As the integrand is zero, so the integral will also be zero. And with that, we can move back here. As this integral is 0, we simply get this result. So part B is also solved. I hope you get my idea. Now let's move into the part C of the problem. In part C, it says to consider the current sources generated by time harmonic, point electric dipole sources. At some position R1 and R2. So this generates Z1 and this generates Z2. And for that physical scenario, we need to prove where P2 and P1 are just point electric dipole moments. For point electric dipole sources, the charge density can be written in this way. I'm not going to prove it here, but you can check Andrew Jangwill's book Modern Electrodynamics for the proof. You can see in the screen the section number for this proof. And as the point dipole is situated at some position R1, we're going to get a delta function here. So this is the expression for the one dipole. And for the other dipole, we're going to get the charge density like this. But as you can see, this has no position dependence, so we can take this P2 term inside the divergence term. And similarly, we're going to have a similar relation here also. So these two relations are actually valid for any time-dependent point electric dipole source, but not for only time harmonic ones. But how to get the current density here? That's the actual quantity of interest, right? So to get the current density, we can use the continuity equation. Remember, the continuity equation connects the current density with the charge density. So using that, we're going to get the current density from these two dipole sources. So for dipole 1, let's say we're going to get Z1 and ρ1. We're going to get this. Okay, and so we're going to write D, and the expression for ρ1 is like this. P1 T delta centered at position R1. And there's a minus here. So we're going to get the time derivative over this P1 here. Now, as you can see, there's a divergence on both sides, so we can just equate the terms inside it. So we get Z1 equals to P1. And remember, we have assumed that this time dependence is harmonic time dependence. So P1T will actually be something like this. So if you take the time derivative here, what you're gonna get is just a simple scalar factor in front of it. So with that relation, we're gonna just get this. And for the J2 current density, we get a similar relation. But the Dirac delta function will be centered at R2 position. Now use these relations into the result that we found in part B. So in part B, we actually got this relation here. So we're gonna just put the expression of Z2 and Z1 here. So what we're gonna get? Minus I omega P1, sorry, P2T delta R2 dotted with E1. On the right side, you're gonna get a similar relation. Dotted with E2. Now, using the shifting property of the Dirac delta function, we're gonna get the value of the integrand at point R2 from this integral. So what we're gonna get is P2t and dot with E1 at R2. Similarly, on the other side, we're gonna get P1t and dotted with E2 at R1. Now cancel out the minus I omega from both sides and let's write P1 with the time harmonic dependence here dotted with E1 R2 with E2 harmonic time dependence dotted with E2 at R1. Now you can cancel out the harmonic time dependence terms and you're going to get the result that we wanted. So that's part C solved. I hope you got the ideas that I have used in the video to solve the problem. Hope you enjoyed the video, and if you did, please hit the like button, subscribe to my channel, and share it on your social media links. That's all for today. Until next time, keep solving problems.